Hey everybody, my name is Julius and welcome back to Fastware. So today I want to discuss a very controversial topic, a premature optimization and understanding the resource limits of any given hardware. I know some people getting triggered immediately, already trying to write some comments. Wait, I'm gonna handle that. You can still write your comments. It would be lovely to hear from you. Anyway, so we are implementing our little toy application. You saw the spheres being rendered all the time. Now, what I wanted to do today is look at actually how things perform and how to measure that performance. And are we improving? Are we getting better? So that's the topic for today. So I refactored our code a little bit to kind of reflect more of what I want to see, kind of a more easier flow, not more easier, but easier flow from the main. So basic definition of what we're doing, initializing our loggers, our control blocks, our frame limiters, debug, creating windows, setting up shaders, setting up structures, because currently everything's cons expert, so I can do that. It's lovely. So vertex data where we have positions, normals, and UVs, our indexes, preparation matrices, and basically all preparation data. So the model, the animations, the speeds of each of the models, how they rotate and whatnot. And then the GPU matrices, which are the model matrices and the normal transforms. So you remember earlier, we had the code for inverse transpose matrix in the GPU. Now I moved it out of the GPU and it is sitting on the CPU. It's pre-computed in advance and being sent to GPU to give it more time. So the code tends to flow a little better, and we have our main loop where I'm sure you immediately can see that we have the new metric kind of macros, which are now littering the code. Now, what these lovely things do, it allows you to instrument your code and understand each section of the code or each function as to how many maybe milliseconds or microseconds that particular part takes. This is implemented using a stopwatch. So a stopwatch is a little class which, when you initialize it, it starts the timer, records function name, context name, and a start time. And then obviously when you destruct it, it takes the current time minus the start time and then prints out the duration that that particular section of code took. So the way I am using it is, as you can see, I'm creating kind of a virtual scopes and then introducing the metrics, so to measure each section individually, and then the entire thing with the render loop. So how does it look when we're running? So as we start our application, running for a little while and then exit, you can see that each particular thing is logged as a metric, and then we can see, so processing events, so the polling event section right here, which just measuring how long it takes to poll. Then the next thing is our prepare models. So prep models is updating our transforms and GPU matrices. Then our render frame, which sets up all the necessary variables and then copies the GPU data from those GPU matrices into its appropriate GPU buffers, renders the target, ends frame, and then you have swap buffers. As you can see, the polling, processing events, super fast. Pairing models, about 1.5 milliseconds, rendering frame, about half a millisecond, and then swapping buffers is super expensive. Obviously, because as you swap the buffers, it submits all your render requirements to the GPU to do the actual work, right? So when doing that, with instrumentation, you can see each part of the code quite clearly and what's happening where. But I want to show you that when you rely on the external tools and only on the external tools, you might get kind of a skewed image of what's actually happening. So I'm going to be using Perf. I'm sure you all know about Perf. It's a great little tool, sampling profiler. I've done a video in the past. You can find the card in the corner so you can check it out. So what we do, we have our kind of a path to our application, and what we're going to do is perf record -g. So perf record says I want to record a call graph, and then measure the amount of times that particular section of code is being executed, and come up with some percentages of how much time is being spent in that particular section of code. So perf record -g, my little toy application. And then we can basically navigate for a little while, see what's happening here. All wonderful, test our different kind of modes for rendering, and exit. Now what perf does, it says how many samples it recorded, to which file, and what's the size and whatnot. So after that, you can do perf report. And then if you recorded with -g, you put the -g in the report as well. And you can see the output of the perf. So perf kind of says that GPU matrices and update transforms. So this is about 12. This is about 27. So together it's what, 39, so almost 40% of my toy application is spent in the in the CPU, right? Computing these matrices and updating transforms. But we already know by looking at this prep models that that particular code takes about 1.5 milliseconds, which in the context of a game is fairly significant transformation. However, it is not that big compared to 16 milliseconds. We for sure know that that's not 40%. So 1.5 and 16.6 milliseconds, that's definitely doesn't add up. Something doesn't add up. And the reason why it doesn't add up, because of this swap buffers, right? Because part of the code in swap buffers are actually right here in this GL core, but the rest of it is basically waiting for geometry to be rendered so the next frame can begin. And to understand that, it's like, you cannot just pull that number out of, you're behind. What you want to do is actually understand and see that your GPU is actually being utilized to 100% to make sure that you're not kind of assuming things before you actually measure. So let's not assume things. And I have a little tool which I downloaded. On Linux, it's called the NVTop. I have it running right here. So it basically measures the GPU utilization for any given process, and tells you what kind of a device you have, how much memory, all that good stuff, right? So you can see that I have a NVIDIA GeForce GTX 1070. And I have currently, my UI utilizing a little bit here as well. So now what happens if I start my application? So I start my application and I look at that graph, and we can see that my GPU, so this is that game, starting to utilize close to 100% at all times. So that means the amount of geometry I'm sending to the GPU through shaders and whatnot to transform, it's immense. It's basically saying, I reached my limits. So using multiple tools to understand multiple things, including the instrumentation in your code, is actually critical. But now, are we happy with rendering 1,000 instances of an object? This is basically a single rendering pipeline. and we have 50,000 instance objects rendered, which, if you know anything about GPUs, rendering instances of exactly the same thing, which share exactly the same geometry, just transformation matrix is different for them, is the fastest way to render anything, right? And we can only render 50,000 of them. Is that good enough for us? Are we happy with that kind of a performance? I would say no. And this is where I would say I can shut down the conversation about premature optimization quite I can debunk it quite thoroughly. Because without doing these tests early in the project, you can make a decisions for that project which will end up hurting you in the long run. Once you've written most of it, you cannot retrofit performance into your system. It is very, very difficult to do. So, but it's much easier to measure early to understand the limits of hardware that you're going to be running on and say, okay, so if I'm reaching limits at that level, therefore I can do some clever techniques to expand my performance characteristics to allow more objects to be rendered. Maybe not more geometry, because I can render about 500 million, I think, triangles, but hey, that should be good enough if you do smart things. So I've been researching a little bit about what smart things we can do in order to alleviate our hardware limits. And the thing that came up is geometry culling. So normally the GPU itself does some geometry culling. That is called the back face culling or front face culling, and you can just pass in a specific kind of a call face function, and then where do we want. So back, and then the depth test. This is also a small kind of a thing that eliminates some geometry from the GPU. However, majority of work we need to do. And I think the tool, the algorithm that I found that we will be working on for next time, and that's what I'm going to be looking to do, is called the Octrees, right? You can see the graph and representation in the corner. It's basically a way of partitioning your three-dimensional space into smaller sections, and it allows fast queries on, where are the objects. Now, how does that actually help us? So the way we can use this is say, okay, we want to limit, imagine you're looking at something and you don't want to render anything that you can't see right here or something that's behind you. What for, right? You're just submitting geometry which is never going to be visible to the user. So what we want to be able to do is say, okay, so this is my view, so the frustum, right? We have a near plane and we have a far plane, something that's, far enough. And then we have these side planes and top and bottom planes. So your camera produces a frustum, kind of a prism object, and you want to be able to say, given these 6 planes, give me all the objects that I can see, right? And therefore eliminating all the objects that you can't. This is one way of saying, reducing number of objects that you even need to submit to geometry, to GPU, to render. So that way we can basically speed up our performance and allow more objects to be in the scene, but not always submitting them to render, therefore maybe improving our performance. So that's one thing. That's for our camera. Another thing that we can do, which is pretty cool, is basically the further something is, the less geometry you take to render. So something's really close, maybe have, like our little spheres, 1,000 triangles to render. But if that sphere is like, really far away next to the backplane, right? So you have a near plane and a backplane. So the near plane, really high resolution, many kind of a triangles, and really far away, you might need only like 10 or something that almost looks like a sphere, but not really is. Just a blob. Or even you render two triangles with a little image that you kind of put in there of something that looks like it rather than actually rendering real geometry. So that is known as level of detail. So LOD. There's a couple of links that I will leave in the description if you want to read about it. The premise is like that. You submit all your geometry, but then your indexes denote which vertices to take. So when you have three adjacent triangles, you say, okay, so instead of rendering 3 of them, I'll say that only these 3 points, and that is my one triangle rather than 3, and reducing number of geometry that needs to be processed by the pipeline. So this technique is level of detail and allows you to kind of reduce number of geometry transformed the further the object is from the viewer, from the camera. So next time we will be building these sort of systems. To enable Octrees, we basically need to have also a technology known as bounding box. So given a set of geometry, you need to compute a bounding box for it to basically be able to tell the Octrees efficiently that this entire object is in there or partially or whatnot. So that's what we're going to be doing next time. We start with a bounding box and then slowly we'll be progressing by implementing the Octrees and the calling techniques that we've been talking about. So I hope you're excited about learning about these things. I know I am. This is the first time I'm doing these sort of things. It's kind of a crazy algorithms. They're all CPU based, so not a lot of GPU stuff, but a lot of CPU stuff. So just solving really cool problems. If you're excited, please subscribe. Leave your comments. I'm really interested to see if you like the progression of the project and what do you think about premature optimizations. I know it's a controversial topic and you know my position on it. And with that, thanks for watching and have fun writing fast code. Cheers. Bye.